displacement reactions. These are redox reactions where metal displaces hydrogen from acid or water. Like, for example, magnesium and hydrochloric acid. The magnesium will kick out the hydrogen, making bubbles. You might have done a reaction like this in Chem 1. Okay, I can't do this anymore.
I kept a straight face for a little while, but the helmet's a little too small for my gigantic head. Alright, there will be some meowing because Three-Legged Kitty is back. Alright, so certain metals can kick out hydrogen from an acid, and certain metals can even kick the hydrogen out of water, and instead of forming a salt, you'll get a base in hydrogen gas. Now, how do you know if this is going to happen? Well, that is what the activity series is for. So this isn't the complete one you'll get in your notes, but this is a simplified one. Basically, the more reactive metals are towards the top. So see where hydrogen is here? From lead all the way up to lithium, it can kick hydrogen out of an acid. Now, from iron all the way up, they can kick the hydrogen out of water if it's steam. And then only the top 5 from sodium on up can kick the hydrogen out of pure water, just at room temp, cold water. Alright, so basically this is just a list that helps you determine who can kick out who, or whom, not sure of the grammar there, who can kick out another element in any type of reaction. So if the single element is above the other guy, then that means it can kick it out and steal its anion girlfriend, basically. All right. So these are called single displacement reactions. An ion gets displaced by another element. And so the pure element is oxidized where the ion gets reduced. So I just got to show you some for that to make sense. So here's an example of a single replacement reaction, also known as cation replacement. If that sounds familiar, cations are what we call positive ions. And so in this example, copper goes from being neutral to being too positive. So he's oxidized and becomes a cation, a positive anion. So this is cation replacement. So in this reaction, what they've done is put a coil of just neutral, pure copper in a clear solution of silver nitrate. Now, because copper is above silver on the activity series, the copper can kick the silver out and turn it into a neutral element. And that's what all this fuzzy stuff is here. That is the silver getting kicked out of the solution. And then the copper now forms copper nitrate, which is soluble in water, and that's what this bluish hue is about. That's copper nitrate being dissolved in the water. All right, now, on the other hand, can we get the reaction to go the other way? Can the silver kick the copper out? No, this X is supposed to be up here on the arrow. Not sure what happened there. This reaction cannot happen. Silver is below copper, so it can't kick the copper out spontaneously anyway, without the addition of energy. So the reversible reaction is not possible. So here is a video. It's a time-lapse video, but it's still kind of long, so I'll probably just skip forward. But there they've got the copper and the silver nitrate, and you can see the copper darkening, and that's no longer copper, actually. What we're seeing is silver developing on the copper, and then you can see the bluish tint. That's the copper nitrate dissolving in the water. And then by the end, it looks hairy with silver all over it. Now, a lot of times students will say, cool, we made silver. Can't we sell this and make money? We'll be rich. But here's the thing. There was silver in there all along. It just was in that clear solution. And trust me, silver nitrate is not cheap. You pay for that silver when you buy the silver nitrate. I'm going to have to buy some for our silver-plated test tubes we're going to make for the holidays a little later on. And I'm paying the equivalent amount for the silver I'm getting, trust me. And then we will kick the silver out and it'll stick to the glass inside the test tube and it'll look really cool at the end. Instead of like this kind of moldy, hairy looking thing, but you'll just have to trust me that that is silver. And then now the solution's really blue. You can really see there's a lot of copper nitrate in there. All right, so here is the activity series that is in your, which one is it in? The guided reading, I believe. It's also, there is a simpler looking activity series on your periodic table packet I gave you earlier in the year. So once again, lithium's on top. Technically, potassium, like we think of potassium as being more reactive than lithium. I mean, potassium spits out purple flames, and there's so much energy that it ignites the hydrogen that's being formed, and it goes kabooey. Yeah, that's really the sound it makes. Lithium doesn't do all that, but it happens faster because the lithium, as it gets hot, melts, and it reacts even faster. And so lithium's usually considered more reactive, even though visually it doesn't look nearly as cool. All right, and then notice down here at the bottom, poor little old gold and platinum and silver, and they can't really kick anybody out, and that's a good thing. That's why we make jewelry and silverware and such out of them, is because they are so unreactive. You wouldn't want your spoon dissolving in your chicken noodle soup. At least I wouldn't. All right, so here's another one. This is one of my favorites to do. It's magnesium ribbon. This coil here is the pure magnesium. It is neutral initially, and then if you put it in hydrogen or hydrochloric acid, the magnesium will kick the hydrogen out, and you will end up with hydrogen gas bubbles. And the magnesium will become magnesium 2+, so it will be oxidized. Its charge will go up, and the hydrogen, which is originally +1 in the hydrochloric acid, will go down to being just neutral H2 molecule, so its charge will be reduced. So notice, once again, these two always happen together. One atom gets oxidized, the other one gets reduced. What's fun to do is put a balloon over this reaction and gather up the hydrogen and then set it on fire. It doesn't feel real good on the ears, but it's still fun. Oh, I'm not trying to open a file. I'm just trying to go forward. Okay, so looking at your activity series, which one is more easily reduced? The magnesium 2+ or the nickel 2+? Okay, well, going back to the activity series, okay, what it's asking isn't who's easier to oxidize. That's how this is written. It's actually asking the opposite question. Which one's easier to reduce? Which one is it easier to go the other direction? Okay, to get it to gain 2 electrons. So what were our choices? I already forgot. I think nickel was one. Nickel and magnesium. Okay. This time, if you're looking at being reduced, we're going to look at the activity series the other way, okay? This is a list of who's best at being oxidized. So lithium is the best at being oxidized, and gold is the worst. But on the flip side, if we're looking at ease of being reduced, gold is the easiest to reduce, and lithium is the hardest to reduce. So between nickel right here and magnesium up here, nickel will be easier to do the opposite of this reaction with. It's easier to get nickel to gain 2 electrons, nickel ions to gain 2 electrons and become neutral nickel. Okay, so that's why that one is the winner. It's easier to reduce it. All right, writing balanced molecular and net ionic equations for redox reactions. Same rules apply. Your spectator ions are going to be the ones that didn't change state and didn't change their charge. Okay, let's see if I have it up here. Okay, so here's just the balanced chemical molecular equation. Aluminum solid, thrown in some hydrobromic acid. I'm sorry, I got cat hair all over my face. Solid aluminum, put in some hydrobromic acid. Aluminum is above hydrogen on the activity series, so it will kick the hydrogen out. Here is the hydrogen all by itself. And then the aluminum will hook up with the bromine, and we'll have aluminum bromide, and then it'll promptly, dissolve in the water. So it's AQ. So who actually changed here? Well, did aluminum. It was solid with no charge. Now it's aqueous with a +3 charge. Okay, there is our element whose charge went up, so that's oxidized. Then hydrogen was +1, sweet pea. Sorry, cat fight, possibly brewing. Hydrogen was +1 in the acid. Come back. And aqueous, okay, and now it's neutral and a gas. Okay, so that was the one that was reduced. Aluminum was oxidized, hydrogen was reduced. What did bromine do? Not a thing. Bromine was -1 and aqueous in both the reactants and the products, so that's our one spectator ion that we can ignore and leave out. So here is the complete ionic equation. Remember, you bust up your strong electrolytes. You leave the covalent stuff together, like the hydrogen here, but your soluble ionic compounds and your strong acids and bases, you bust up into ions, make sure that it's balanced, make sure you show the charge and the state, and then for the net, you get to leave out the bromine ions because they didn't do anything. All right. Okay, so we'll do this one in class. It's kind of hard to talk you through it. Skipping. All right, so that's it for redox reactions, single displacement reactions. We can also figure out who's oxidized and reduced in combustion reactions, decomposition reactions, synthesis reactions. It's just the activity series only helps us predict whether or not single displacement reactions will happen. Combustion reactions, shoot, it'll burn. Okay? So there's no guesswork to that. And the synthesis and decomp, if you get stuff hot enough, you can usually get it to happen. So we only need the activity series for single displacement reactions, a single element trying to kick out another one. All right, that's it for redox. Now for my favorite part, the stoichiometry, the math.